Hi everyone and welcome back to my channel in Economist. So in the previous video we have covered what is limit of a function and we have also solved couple of questions on that. Today we will be starting with the continuity of a function. So let's start with the basic concept. What is continuity? Continuity comes from the word continuous, which means that without any break or without any gap. If the function has no break or gap, if the graph of the function has no break or gap or a jump, then it is said to be continuous. For example, let me show you this. Suppose you have the axis like this, x-axis and y-axis, and you are drawing a function like this. Now, while you drew this function, you haven't lift up your pen, right? It is a smooth continuous graph and you don't need to lift up your pen in order to draw this, right? So, if this is the case that the graph of the function can be drawn without lifting your pen, we will say that this is a continuous function. It is the other way round of saying that the graph has no breaks or jumps or gaps, right? You can take another examples also. Suppose it is a linear function like this. Here also you don't need to lift up your pen while drawing this graph. So it is also a continuous function. But what if I say, suppose the graph is like this and this is suppose a value say 2. Your graph look like this. You draw this part and then here you have a jump and then again the function starts from this point and it goes like this. Suppose this is your function gx. Now, in order to draw this function, what you have to do, you have to draw this segment first, then you have to lift up your pen because this is a discontinuous part here. And then again, you are continuing from this portion, right? So, this is an example of discontinuous function. Why it is so? Because you cannot draw the function without lifting your pen. That is what I have written here, that a function is not continuous, then it is called a discontinuous function. Okay, now let us take an example. Look at this function. The function is f(x), which takes the value 1 if x is less than equals to 0, and it takes the value 2 if x is greater than 0. Now what you have to do, you have to check the continuity of this function at the point 0. Why 0? Because we always take the breaking point while checking the continuity. If you are talking about continuity at a particular point, you will always take that point in the domain, which basically divides the interval into two parts. Here the value is 0. So if you draw the function, what do you think? Do you have to lift up your pen or you could draw a smooth graph? You could take a pause and think about this. Okay, now let me show you this graph. This is the graph I am talking about. So when x takes the value less than or equals to 0, it means this portion, right? Also this value is included. The value is 1, functional value is 1. So you have this as the graph, the blue line. And at the point 0 also the value is 1. So here you have a filled circle. But as soon as x is greater than 0, that is this portion, what happens? The functional value becomes 2. So it starts from here. It is a discontinuous point because at the point 0 the value is 1 and not 2. So it will be an open circle and then the graph looks like this. So this is the blue graph you have for this function. Now if you look carefully, again this is a discontinuous jump. There is a jump. So you cannot draw this function without lifting your pen, and that will give you your answer that this function is not continuous, right? At x equals to 0, the function is not continuous because from the left hand side if you see, it approaches to the value 1, and from the right hand side if you see, it approaches to the value 2. But it cannot take the value 2, but it approaches towards the value 2. If this is the case, then the function is not continuous. Again, see this example. If x takes the value 1 if x is not equals to 0, it means that x can either be greater than 0 or not, or less than 0, and it takes the value 2 if x is equals to 0. Now again what you can do, you can draw the graph and see for yourself that except the value 0, the graph takes the value 1. At the point 0, it takes the value 2. Again, if you have to draw this, you have to draw this line first, then take a jump, lift up your pen, draw this circle, and then you have to come back and draw this line. So again, it says that it is not continuous. So what is continuity? If you want to know the formal definition, this is the definition, and this is the only thing you need to know on this chapter, because this will give you solution to majority of your sums that you will do. Let me show you. Suppose if is a real function on a subset of real numbers, and let's see be a point in the domain. So if you are, now we are talking about continuity at a particular point. Later on we will come to what will happen in an interval, but as of now we want to know what will be the definition of continuity of the function f(x) at the point x equals to c. Now the criteria for that is that limit x tends to c f(x) should be equals to fc. What does it mean? It means that the limit of the function at x equals to c has to be exactly equals to the value of the function at x equals to c. So if you know this thing, you know the entire chapter. That limit of the function, if you haven't seen my video on limit, then I will give the link in the description. You can see that and revise your concepts, and then come back to this, that limit of the function at x approaching to c will be exactly equals to the value of the function at x equals to c. If this is the case, you will say that the function f(x) is continuous at the point x equals to c. Right? I hope this is clear. Now let me solve some questions with you. Check the continuity of the function f, where f is given as this at the point x equals to c. So all you need to check is that limit x tends to 1 f(x) is equals to f1 or not. This is what you need to check. If this criteria is satisfied, you will say that the function is continuous. So let's do that. f(x) will be limit x tends to 1, 2x plus 3. So put the value 1 instead of x, it will be 2 into 1 plus 3, which is 5, right? And then what will be f1? For f1 also you have to put the value 1 here, so it will again be 2 plus 3, which is 5. So you have proved that the limit or limiting value is equals to the functional value at the point 1, and the value is 5 here. So this function is continuous at this point x equals to 1. I hope this is clear. Again, for example 2, you have to check if the function f(x) equals to x squared is continuous at x equals to 0 or not. Again, the process is the same. Do this. This is limit x tends to 0 x squared, which is nothing but 0. You are putting 0 instead of x. And what will be f0? f0 is simply put the value 0 here, it is also 0. So the limit of the function equals to the value of the function, which is equals to 0. So again, this function is continuous. Okay. Let me solve another question. Discuss the continuity. f(x) is mod x at x equals to 0. Now for the mod, what you have to do, you have to first write the simplified version like this. By this time you must know this, how to write mod in this way. Okay. Now since you have to find the continuity at x equals to 0, but this range, the domain of this function is divided into two different parts, you have to check both the left hand limit and the right hand limit. Right? In the previous cases, you are checking this, but there is no division in the domain, so you can just simply do this. But here, since you have the functional form is different for x greater equals to 0 and x less than 0, you have to check limit x tends to 0 plus f(x) and limit x tends to 0 minus f(x) as well, right? So do that. For positive portion, this is x, so the value is 0, and for the negative side you have 0 minus x, this is also 0. And what is the functional value at 0? This is the range you will consider. Put 0 here, it is 0. So the left hand limit, the right hand limit and the functional value all are equal. So it says that the function is continuous. So the mod function is continuous at x equals to 0. Okay. Now here I have listed some of the examples of continuous functions that you will encounter many a times. You can take a look at this. Any identity function, any constant function, any polynomial function, trigonometric functions like sin x, cos x, any exponential function, logarithmic function, hyperbolic functions, and also absolute value functions like mod x plus mod x minus mod x mod x. So these are all the examples of continuous functions. They will be continuous in their domain, right? And here are some examples of the functions which are discontinuous. And also I have mentioned the points of discontinuity. So box x, this we will see in our example, that box x is discontinuous at every integer in its domain, right? It's a very important thing. We will show this in a while. Also x minus box x, that is also discontinuous at every integer. 1 upon x is discontinuous at x equals to 0. You can try to prove them by yourself. It's very simple. Also, if you see this trigonometric functions, they are discontinuous at these points. E to the power 1 upon x is discontinuous at x equals to 0, and hyperbolic function is discontinuous at x equals to 0. So you can take a look at this, you can take a screenshot, and you will encounter this many a time. So get yourself familiar with this. Okay, and now these are your homeworks. Example 4, 5 and 6, you can also take a screenshot of this page and solve this. This will give you more clarity on this. Okay. Now by this we have finished continuity at a particular point. Now we will move to continuity of a function in an interval. What if you are given an interval and you need to find a continuity on that? What will you do? So look at this definition. A real function f is said to be continuous if it is continuous at every point in the domain. Suppose you are considering a function f which is defined on the closed interval a to b. So the function is like this. F is a function which has a domain from a to b, and suppose the range is r. Doesn't matter. So you are only concerned with the domain, and you need to check that if f is continuous in this domain or not, in this entire domain or not. So what you will do here is that for f to be continuous, it needs to be continuous at every point in the domain a to b, including the endpoints a and b. So this is a very important aspect that you need to remember, that for continuity in this interval, the function has to be continuous at every point in the interval, including the endpoints. That is, endpoints are a and b here. And how to check that? Continuity at point A. Suppose you start with this. So start with A. This will be the criteria of continuity. Limit x tends to a plus fx is equals to fa. So again, the criteria is the same. The limiting value equals to the functional value at that point. Similarly, you will do the same thing for the endpoint B. Limit x tends to b minus fx is equals to fb. So check this. If they are equal, then you will say that the limit exists and the functional value are equal. Also, you can take any point in between, and then you can check the continuity at that point also. Because if you suppose you are taking any point c, which is a real number and which belongs in this interval a to b, and c is not equals to a and c is not equals to b. So if you can show that for limit x belongs to c fx is equals to fc in this particular range, then also you will say that the function is continuous in the interval a to b. So you have to check three things. You have to check if these two things are equal. Firstly, calculate this in this particular values, and if you see that they are equal, then take any random point and check the limit at that point. If it is showing the same value, the limiting value equals to the functional value, then you are assured that the function is continuous at that particular interval. Now let me show you some questions on this. So the function is fx is mod x. Is it a continuous function? Now previously, if you have seen, I have shown that the function is continuous at the point x equals to 0. This has already been proved. So what else you have to show? You have to show that fx is continuous. So at this point this function is continuous at 0. So I have to show that this function is continuous here, that is at the range x greater than 0, and also you have to show that this function is continuous at the point when x is less than 0. So this box has the give me a minute. Yeah, so range is the domain is from minus infinity to infinity, and the function is like this, right? And what you have to do, so you have to consider two cases here. Case 1 is that you are considering for the range x is greater than 0. So what you have to do, you have to say that there exists a value c1 greater than 0 such that limit x tends to c1 if x, that is limit x tends to c1 box x is equals to box of c1 which is equals to if c1, right? This is the case 1, which shows that the function is continuous when the domain is x is greater than 0. So if you are considering only this portion, so you can show that there always exists a real number c1 which is greater than 0, for which the limit of the function is equals to value of the function, right? Also, if you consider case 2, you are taking the range x is less than 0, then also you will say this, suppose this is c2 is less than 0 such that you are taking a random value c2 which is less than 0 such that the limit of the function is exactly equals to the value of the function, which is box of mod of c2, sorry. So if you can show these two cases, then only you can say that the function is continuous, and this is true for the function mod x. You can take any value, take 1 2 3 4 or any value in decimal, you will see that these conditions hold true. And why I am choosing this random numbers, because I have to show that in this interval and in this interval the function is continuous. So you are randomly picking up values. Here I have randomly chosen a value c1, here I have randomly chosen a value c2. c1 is greater than 0, c2 is less than 0, and if I can show that the function is continuous at these random points, then I am assured that the function is continuous at every point in this particular domain and in this particular domain. I hope you got the process. If you have any questions on this, you can ask me in the comment section. I'll give reply to that. Okay. Now, see example 8. Discuss the continuity of function f, where f is this. It's a polynomial function. Pretty clearly you can see it's a polynomial function of degree 3. And we have already discussed in the chart that polynomial functions are always continuous. But still we have to show this. So for this function, first determine what is the domain. What is the domain of this function? Domain is all the real numbers. So lies from minus infinity to plus infinity, and the range is also real number. So what you have to do, you will say assume there exists a real number c. There exists a real number c for which limit x tends to c if x is exactly equals to if c, which is equals to cq plus c square minus 1. So limiting value is equals to the functional value. This is true for any real number that is in the domain of this function. So we'll say that this function is continuous. Any polynomial function is continuous, but if you have to prove this, you can show in this way. right? Okay. Example 9, discuss the continuity of the function f, where fx is 1 upon x, x is not equals to 0. So what is the domain of this function? The domain is any real number except the value 0, and the range is this, right? So you have to consider, so you will say that there exists a value c which belongs to real number except the value 0, such that limit x tends to c fx is always equals to fc, which is equals to 1 upon c, right? C cannot take the value 0, so this fc will be exactly equals to the limits, and the limiting value will be 1 upon c. So again, this function is continuous. Okay, now this is, I want to give you homework, and you will see here is that this function will be discontinuous. Let me give you a hint how to do this. So here you see that the breaking point is 1, and you have two ranges, x less than equals to 1, x greater than equals to 1. So you have to find out limit x tends to 1 minus fx. This is the left hand limit. Limit x tends to 1 plus fx. You will find the right hand limit, and if you see these two are equal, only then you have to take any value. So suppose this is 1, and you are finding this and this. If you see these are equal and they are equal to f1, that is the functional value, then only you will say that the function is continuous, otherwise it is not. So find the left hand limit, find the right hand limit, and check if these two are equal or not. And if these two are equal, then check if that is equal to the functional value or not. If these three things are equal, you will say that the function is continuous, otherwise it is not. So please do this. Okay. Now what I told you earlier, that I'll show you the proof of this, that find all the points of discontinuity of the greatest integer function defined as fx is box x. Box x denotes the greatest integer less than or equals to x. Now for that, what you have to do, firstly see this graph. I have described what is greatest integer function in one of my videos. If you haven't seen this, I will give the link in the description. Please go through that, and if you see that video, you will know that the graph of the function looks like this, right? And now you have to find out the points of discontinuity. How will you do that? You have to consider two cases here, case 1, case 2. In case 1, what you will do, you will take the values of c which are real numbers except the integer values, right? You will consider c in the domain of the function. Domain is from minus infinity to plus infinity. You will take a value c which will be a real number but which is not an integer. This is the first case. Suppose I take the value to be, say, 0.5. This is a decimal number, it is a real number but it is not an integer value. Now check the continuity at this particular point. So what you will do, limit x tends to 0.5, box x, right? This will be what? This will be box of 0.5. And if you know how to find the box value, here you have 0.5. So the value will be the integer on the left, right? Integer will be 0. The greatest integer on the left hand side is 0, so the value will be 0. And find out the functional value. Functional value at this is f of 0.5, which is also 0. If you know the process, you will find it simple, that what you have to do is that just check the integer on the left hand side, the immediate integer on the left hand side, that will be the box value. So here if you take c to be in this particular case, in this particular domain, that it is a real number but it is not an integer, so you can show that the limiting value is equals to the functional value. I hope this is clear. You can check it for yourself. You can take any value, just leave the integer values and take any value in the domain. You can consider, take it from this side also, take any value, and you will see that the limiting value is equals to functional value. So what we can conclude from this case is that the function, the greatest integer function, is continuous for any value which is not integer, any value in the domain which is not integer. Now let us consider case 2, where we will consider another random number, say C1, which is or which belongs to the set of integers, right? Suppose C1 takes the value 2. Let me erase this. Suppose C1 takes the value 2, then find out limit x tends to 2 plus fx. What will this be? If you consider the positive side, the value will be 2 itself, right? So you are approaching 2 from the right hand side. What will be the value? The value will be 2. But if you consider this side, if you consider it from the right hand side, what will be the value? The value will be 1, right? The greatest integer on the left hand side is 1 here. You can see this for yourself. You can do it on your own as well. So what you see here is that the right hand limit is not equals to the left hand limit, right? Right hand limit is not equals to left hand limit. So if you consider C1, that is any random number from the set of integers, you will see that the function is not continuous. And here I have given you the detailed proof. So this is something I wanted to show you just to, show you with an example. But formally you have to write like this: case 1 and case 2. Where case 1 says C is a real number which is not equals to any integer, and C2 is C is an integer. So what you will see is that it is evident from the graph that all the real numbers which are close to C, the value of the function is equals to box C. That is what we have shown here, that value of the function is equals to, so C is here is 0.5, so the value is box of 0.5, which is nothing but 0 here. That is what you are formally writing here, that if limit extends to C fx is limit extends to C box x is box C. So functional value is equals to the limiting value, and it is continuous at all real numbers which are not integers. But if you consider integers, we can always find sufficiently small real number r greater than 0, for which box of C minus r is C minus 1 and box of C plus r is C. That is what we shown here, that if you consider from the right hand side, you will get that particular value only, C. But if you consider from the left hand side, the value will be C minus 1. You can see from this example also. And that is what we have done, taking an example. Since the limits are not equals to each other, the function is discontinuous at every integer point. And this is a very important proof. Try to remember it, and it will come handy from the exam point of view. Okay. Next, we will move to some algebraic properties of continuity. Let us look at this theorem. Suppose f and g are two real functions which are continuous at a real number C. So these functions are continuous, f and g, at real number C. Then these four properties will hold. F plus g is also continuous at x equals to C. F minus g is continuous at x equals to C. F into g is continuous, and f upon g is also continuous, provided that this denominator is not equals to 0. Okay. Let me show you the proof of the first one, and the rest of the things are similar. You can do it. So the proof is that, start with this left hand side, limit x tends to C f plus gx. So if you know the properties of limits, you can separate these functions and take limit separately on each of these functions. So take the limit inside, limit x tends to C fx plus limit x tends to C gx. Since these functions are continuous, the limiting value will be equals to the functional value. Here also the limiting value will be equals to the functional value, and you can then add this by the definition of f plus g, and this will give you your criteria that here the limiting value is equals to the functional value, right? And this is the criteria for continuity. So f plus g is continuous, and the rest of the things are similar. You can try it for minus, product, and division. Okay. And these are your homeworks. I have given you these three homeworks: example 11, 12, and example 13. You can take a screenshot. You can do it for yourself. Let me know in the comment section what you get, right? And the final proof is this. by this we will end our lecture today, that it says every polynomial function is continuous. I have already shown you using an example that every polynomial function is continuous, but if you have to formally write this, I thought that it is important for you. So it's a very simple proof. You can take a look at this. So polynomial function takes this particular form. So it is px equals to a naught plus a1x plus a2x squared plus a3x cubed plus, if you are considering n degree polynomial, it will be in this particular form, right? Now here n is some natural number, n is not equals to 0. If n is 0, this term will vanish and it will not remain a polynomial of nth degree, right? So this an has to be not equals to 0. Each ai belongs to real numbers, so these are all real numbers, a1, a2, a naught, etc. And clearly this function is defined for every real number. Now you can fix a real number c. Suppose you take, and for every polynomial the domain is from minus infinity to infinity. So you consider any real number which belongs to this interval minus infinity to infinity, and you will see that limit extends to c px is equals to p of c. That is, again, the limiting value is equals to the functional value for any c which belongs to the real numbers, right? If you consider c to be any real number, you can clearly show this criteria. So by definition, p is continuous at c. Since c is any real number, p is continuous at every real number, and p is a continuous function. So from the definition of continuity in an interval, we have told that if the function is continuous at every point in the interval, then only it is continuous in that interval. So here you can show that for any c which belongs to this real number, which is the domain of this polynomial function, then you will say that since it is random, c is random in nature and you have randomly picked up from the domain, so it is true for any random, any value in that particular domain, and p is continuous at every real number and p is a continuous function. And in this way you will prove this. I hope you find this video helpful. I have covered every aspect of continuity in one go. And if you like my video, give me a thumbs up and do subscribe to my channel so that you get the notification whenever I post any video. And in the next lecture, I will be covering the differentiability of a function. Stay tuned, and thank you for being with me.